All right, so hello and welcome everyone to week 5 of interactive live sessions for the course on the fundamentals of convective heat transfer. The course is being offered by NPTEL and it's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I am a PhD scholar at IIT Madras and I am the TA for this course. Like every other week, we shall again be solving some problems together. This week, we had to reschedule our class a little bit. It was a fault on my part. I'm sorry for that. And thanks a lot for joining in today. So, with that, we will get started without any further delay. And so, here's question number 1 of today's session, which is asking us that the condition for a laminar incompressible flow to be fully developed in a circular channel is. Then there are 4 options given below which refer to different physical states of the system that correspond to a fully developed flow in a circular channel. So you have to read this question very carefully, and once you've figured out the solution, you can either type it in the chat box or you can unmute and answer. If you have any doubts regarding the question whatsoever, you're always, free to ask. So these are interactive live sessions. Let's make sure these are as interactive as possible. Okay. So with that, we have our question number 1 for today's session. So it's a laminar and an incompressible flow, and it has to be fully developed. So what is the uh, mathematical form of that? So option A is V equal to 0 and dou U dou X equal to 0. Option B is U equal to 0. Okay, so first of all, let me make sure what U and V are. So X is the axial direction in this circular channel, and okay, this is really not working well. Anyway, so and Y is the transverse direction in this. And this is the channel that we have, and U is the flow in the X direction, and V is the flow in the Y direction. Oh my god, this is so bad. I'm really sorry guys, I'm using a different device today and my writing device doesn't seem to be compatible with it. So my writings might be a bit messier than other days. It's already pretty messy and it will be worse today. So that's a warning that I'm giving you. Okay, so with that, we have our first question of today's session, that what is the condition for a laminar incompressible flow to be fully developed in a circular channel? Is it option A, V equal to 0 and dou U dou X equal to 0? Is it option B, U equal to 0 and dou V dou X equal to 0? Is it option C, both U and V equal to 0? Or is it option D, the gradients dou U dou X and dou V dou X both to be equal to 0? Okay, so we have one answer in favor of option A, two answers in favor of option A. Let's see what others have to say. So this is our circular duct. X is the axial direction, the direction in which flow occurs, and Y is the transverse direction, which is perpendicular to X. U is the velocity in the axial direction and V is the velocity along Y. This is really bad, man. This is the y direction. And v is the velocity along y. So, what are the conditions for a laminar incompressible flow to be fully developed in a circular channel? Is it option A, v equal to 0 and dou u dou x equal to 0, that is u does not vary in the axial direction? Is it option B, u equal to 0 and dou v dou x equal to 0, that is there is no variation in v along the x direction? Or is it option C, u equal to 0 as well as v equal to 0? Or is it option D, dou u dou x equal to 0 and dou v dou x equal to 0? That is, there are no gradients in the x direction. So we have two options, two responses in favor of option A, and we will have a look at the solution now. The solution is indeed option A. So those of you answered, you did answer correctly. So the thing is, in a parallel flow situation like this, uh, there is only u and no v, so v would be identically equal to 0 everywhere. And in a fully for this is true for laminar incompressible flow, and in order to be fully developed, this being fully developed means that there is no further development in the x direction. So as a result, this dou u dou x, sorry, dou u dou x has to be equal to 0, so that there is no development in the x direction. So while it develops, it's still a developing flow, as we know in the entrance region of a pipe. But after that entrance length, when the flow becomes fully developed, there are no gradients in the x direction. As a result, dou u dou x has to be 0. So that's why option A is the correct answer. This is a very simple one which we started off with. I hope there are no questions regarding this one, but in case you have, please do feel free to ask. This is clear, right? Okay. So we will move along. We'll move on to question number 2 of today's session, which is again a simple one and related to laminar flow in a circular channel. So question number 2 is asking us, in a circular channel, the nature of fully developed velocity profile for a laminar flow is what? Is it linear, option A, or is it option B, parabolic, or option C, flat, or option D, exponential? What is the nature of the fully developed velocity profile in a circular channel? And mind you, this is again assuming that it's a laminar flow and not a turbulent one. So we have one very quick response in favor of option B, parabolic. Let's see what others have to say. Okay, another one in favor of option B. So, okay, another one. So we have 3 responses in favor of option B. Let's see what everyone else has to say. Another option B. So option B seems really popular. Option B, 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 there are 4 responses in favor of option B. That is a parabolic velocity profile. So without wasting much more time, we will move on and have a look at the correct solution, which is indeed parabolic. So you all know this is a very simple thing. So for flow through a circular channel, we have learned oh my god. Does this work better? This is really poor, man. Sorry, everyone. Let's take a ballpoint. So okay, so this is known as, oh my, sorry, this is known as the Hagen. What is happening? Ballpoint pen. Okay, so this is known as Hagen-Poiseuille equation. How will I write if it doesn't? This is working fine, eh? Yeah. Okay, now it's better. So this is known as Hagen-Poiseuille equation. Really sorry about this, guys. This is not working properly at all. So yeah, so the flow through a channel, a circular channel, is described by this Hagen-Poiseuille equation, and the equation itself is parabolic in nature. So okay, this is going on and on. It's really difficult to do. Yeah, with much difficulty, I was able to write the equation, and I'm still unable. This is multiplied by 2. Anyway, u0 is the maximum velocity, and u is the velocity at a location r, and it's given by 1 minus small r square, which is the radial distance from the center line, to capital R square, which is the radius of the actual pipe, and this is multiplied by 2. So since we know that the maximum velocity is twice the average velocity in the center. Okay, so maybe the 2 won't be here. Sorry. That's wrong. Yeah. So this is how Hagen-Poiseuille equation is given, and this form gives us a parabolic velocity profile in the laminar region. Thank you all for your patience. My device is really malfunctioning today, so I'm taking an awful lot of time. I'm still trying to figure out how to fix this. Anyway, I'll try to limit the amount of writing that I have to do and maybe talk more about how to solve this. Okay, so we are done with question number 2. If you have any questions, please ask. No questions, right? Okay, so we will move on. We'll move on to question number 3 of today's session, which is now asking us that for laminar flow, the thermal entry length may be expressed as LT by D, where LT is the thermal entry length and D is the diameter of the duct. What is that given by? Is it option A, 50 into Reynolds number into Prandtl number, or is it 0.05 into Reynolds number into Prandtl number? Is it option C, 5 into Reynolds number into Prandtl number, or is it option D, 10 into Reynolds number into Prandtl number? So LT is the thermal entry length and D is the duct length. So what is this LT by D given by? Is it option A, 50 into RE into PR? So Reynolds number here is on the basis of D. So R E D will be given by U D by mu. And Prandtl number, as you know, is the ratio of the thermal diffusivity to the momentum diffusivity to the thermal diffusivity. And what is that given by? Is it option A? So we know that this form is equal to some C into Reynolds number into Prandtl number. CH, which is the coefficient of hydrodynamic entry length. Okay, so no, not here. It won't be H here. This is talking about thermal entry length. So this will be CT. So the value of this CT is what we are looking for here. Is it 50? Is it 0.05? Is it 5? Or is it 10? We have one response in favor of option B, that is 0.05. Okay, so let's see what others have to say. Take your time, try to figure out the solution. Meanwhile, I'll try to figure out how to do this thing better. Any other answers? So this is for laminar flow. What is the thermal entry length given as? So the thermal entry length is LT. This LT is the thermal entry length. Thermal entry length. NPTEL. D is the diameter of the duct. We know that LT by D is given by some form of CT into RED into PR, where RED is the Reynolds number on the basis of diameter, and PR is the Prandtl number. So how will we describe, so what is the exact value of CT so that we can relate this LT by D to Reynolds number and Prandtl number? Is it option A 50, option B 0.05, is it option C 5, or is it option D 10? Okay, so we have two responses in favor of option B, and it is indeed the correct answer, option B. So from scaling analysis, we saw that this number LT by D divided by Reynolds number, Reynolds number, Reynolds number into Prandtl number, this thing to the power half. Writing these small curved letters is what is difficult with this. Larger things are okay. So to the power half, that is proportional to 1 or unity. So this is what it we can predict from the scaling analysis, but from a real analytical solution of it, or even experimental or numerical studies, it has been found that this value is actually not 1, but it's actually 0.223 something, and if we square it, then this 223 becomes 0.05 something something. So that's why this LT by D is given as 0.05 into Reynolds number into Prandtl number. So instead of 1, what we get is 0.223. So it's still a good estimate from scaling analysis, considering how simple and easy it is, but it is not accurate. So in order to get accurate results, we need to do something more difficult than more difficult, as well as more accurate than scaling analysis. But still, we can see that it's not very off. Instead of 1, we are getting 0.2, not something like 20,000 or 0.0002. So this is a case in favor of scaling analysis. Okay. Any questions regarding this one? Or any questions regarding entry lengths or thermal entry lengths or hydrodynamic entry lengths? If not, we will move along. We'll move on to question number 4, which is asking us, in the thermally fully developed internal flow of a fluid with constant properties, the local convection coefficient varies linearly with x. Option B varies exponentially with x. Option C independent of x, or option D is a logarithmic function of x. So the local convection coefficient, which is h of x, in a fully developed internal flow. Okay, so we have one response in favor of option C, that is independent of x. Let's see what others have to say. So in a thermally fully developed internal flow of a fluid with constant properties, the local heat transfer coefficient Hx, uh, option A, varies linearly with x, option B, varies exponentially with x, or option C, it is independent of x, or option D is a logarithmic function of x. Okay, so we have another response in favor of option C, that is independent of x. Let's see what others have to say. I would urge everyone to, respond to these questions. You can either type in the chat box or you can unmute and answer as well, whichever way you feel more comfortable. You're welcome to do so. Okay, so we'll have a look at the solution. The solution is indeed option C, independent of x. So those who chose option C, well done. So let's say this is x and this is h of x. I'll draw a small boundary here, an imaginary line which differentiates the developing zone or the entry length. So let's call this LT to the developed flow, the fully developed flow. I'll call this FDL, FDF, meaning fully developed flow. And h of x becomes constant at fully developed flow. And we will see that it is very high in the entry length. So this is how the variation of hx goes. So in the, as the question asked, in the thermally fully developed internal flow, what happens to the local convection coefficient? So since it becomes constant, this becomes independent of x. That's why option C is correct. And this is true for all kinds of boundary conditions. It might be isothermal or might be constant heat flux, or it could be anything else as well. But once it becomes fully developed, it becomes independent of x. It does not change. Okay. Does that make sense? Is it clear? Any questions regarding this thing? Okay. So we will move along. We'll move along to question number 5, which is asking us in internal flow for constant wall temperature condition. Mind you, I am mentioning a specific boundary condition now, which is isothermal condition. The mean temperature varies how? Is it option A, linearly with x, option B, independent of x, option C, exponentially with x, or option D, none of the above? So this is the isothermal case, the mean temperature or the bulk mean temperature. The bulk mean temperature, Tm, as it was called in the lectures. So how does this Tm vary with x? Is it, okay, so this Tm is a function of x. Is it option A, linearly with x, option B, independent of x, option C, exponentially with x, or option D, none of the above? Okay, we have two quick responses, both in favor of option C, exponentially with x. Let's see what others have to say. So we have three responses in favor of option C, exponentially with x. We'll have a look at the solution. And it is indeed option C, exponentially with x. So why is it so? So as we saw in the lectures, the okay, so I'll try to write it here. Oh man, it will be difficult writing the expression down. So Tm of x can be written as Tw, that is the wall temperature, and it is not a function of x here because we have constant wall temperature. Then this thing plus, I'll write it down here. So it is T, oh my god, Tm comma I, that is the uh, this is the mean temperature at the inlet, minus again T of W, the wall temperature, into now e to the power minus of the perimeter into the average convective heat transfer coefficient divided by m dot into, that is the mass flow rate, then Cp into x. So, forgetting everything, if we just look at the Tmx and x, so that is something like a into a plus b to the power e into minus cx. You see the form, right? So the Tm varies exponentially with x. If we look at the graph as well, so if this is x and this is temperature, so first of all we will try to draw a straight line here, which is the constant temperature Tw, and assuming that, I'll use a different color here, and assuming that the fluid entering the wall is lower than the wall temperature, it will vary something like this. It will try to get very close to the wall temperature later on. So, and practically if it's a infinitely long pipe, only then will the two temperatures become equal. This difference would diminish to zero only at x equal to infinity. Otherwise it will keep getting smaller, but the rate of getting smaller would also decrease. So you understand, right? It will increase very quickly initially and then slow down. Something that is the nature of how exponential functions behave. Okay, is this thing clear? Any questions on this? Okay, so let's move on. We'll move on to question number 6. Now this is a numerical type question, and so let's read the question carefully first and try to understand what it is. The system for heating water from an inlet temperature of 20 degrees Celsius to an outlet temperature of 60 degrees Celsius involves passing the water through a thick walled tube having inner and outer diameters 20 and 40 millimeters. The outer surface of the tube is well insulated. The electrical heating within the wall provides for an uniform heat generation rate of Q dot equal to 10 to the power 6 watts per meter cube, and for water flow rate of m dot equal to 0.1 kg per second, the length of tube to achieve the desired outlet temperature must be dash meters. And we know that bulk mean temperature isn't bulk mean temperature. Tm is equal to 313 Kelvin and Cp is equal to 4179 joule per kilokelvin. This is not required. This is some ambiguous information that I gave. So make sure you understand the problem clearly. So there is a tube like this, and there is an outer wall as well, which is a thick outer wall. So this is how it looks like. There is this wall over here where there is a heat generation, Q dot. And we are told that the outer surface is well insulated. So whatever heat gets created in this zone, this only enters into the tube, and it has into the fluid flowing through it, the water flowing through it. It it can't really escape out. This does not happen since it's well insulated. So within this thick wall, we know the inner and outer diameters of this wall as well. There is some volumetric heat generation there, and that volumetrically generated heat that gets into the flow of water through it, which has an entry temperature of some 20 degrees Celsius. Right. And has an outlet of, okay, not 40, 60 degrees Celsius. So whatever heat has been added to the water must have come from the uh, outer wall. So equating them, we can find out what should be the length of this pipe. We have not said what is the length of it. That L is what you have to find in meters. Same question was also in assignment number 5. Okay. I'm looking at assignment number 5, convective heat transfer in internal flows. Question number 10, right? Yeah, it's similar. So I'm sorry about this. I shouldn't really be giving questions from the assignment, but this one turns out to be the same. Anyway, you can solve it now, and if you have any questions, you can ask. So I'm assuming everyone has done this earlier. Okay, okay. So can we skip this and move along? Or do you have anything that you need to be discussed? No. Okay, so we'll move along. Sorry about this one. Okay, so now we have question number 7 of today's session, which is asking us that at a particular axial location, the velocity and temperature profiles for laminar flow in a parallel plate channel has the form given over here. So uy is equal to 0.75 into 1 minus y by y naught whole square, and the temperature profile is of the form 5 plus 95.66 into y by y naught whole square minus 47.83 into y by y naught to the power 4. So these are ugly equations. Anyway, so using these two profiles, you have to find out what would be the bulk mean temperature. This involves a lot of maths. If I try doing it, it'll be a nightmare. Let me see if there is any other way. Meanwhile, you guys try solving it. I'm trying to see if I can find some other way to type this out, because today has been really difficult. Okay, maybe we can do it this way. Okay, so I'll share a different screen now. I'll stop presenting this and we will have a look at this one. Try to bring this down here. Yeah, you're able to see the screen, right? So focus on this left side of the screen. That's where the equations are going to be. Um, so according to the question, we had some u as a function of y and t as a function of y as well. So first of all, we have to find out the mean u as well as the bulk mean t, right? So our equation of Tm is given by something like this. So it's 1 over um into area multiplied by integration of, okay, so in this case it goes from minus y naught to y naught. It's a parallel plate channel, so our integration would also be from minus y naught to plus y naught into uy ty, uy ty and dy, right? So this first equation up top is what the equation of Tm is. Right? Then we are going to look at how to find out this um in the denominator. So that is equal to, sorry, okay, this is not right. I'll utilize this. Uy dy. Keep looking at the equations on the right side of the screen. Okay, that's where things are. So yeah. So should be okay 1 over A. Should be 1 over area into the integration of uy dy, which is the flow rate through the entire area, and the limits of integration go from minus y naught to y naught, and we have the okay, and the area would be equal to 2y as well, 2y naught, assuming unit width. Okay, so now we will simply plug in the above equation. Instead of uy, we will now write down the actual form of uy, which is 0.75 into 1 minus y by y naught whole squared. Okay. So then if we integrate over this, so 0.75 will come out, 1 will become y, which becomes 2y naught. So let's write this. Uh, 0.75 I'm taking out, so it will be here. Then if we perform the actual integration, the first term 1 would become y, and y would go from y naught to minus y naught, so that will give us 2y naught, and minus this thing, this is y, this will become y cubed by 3, and y cubed by 3 will be so it will be 3y0 cubed minus of minus 3y0 cubed, so that becomes 6 into y0 cubed divided by y0 square, so that is again 6y0, right? uh, okay, no, sorry, 1 by 6, right? That will be y0 by 6 by 3, sorry, it will be 2, and wait a second, am I doing this correctly? It will be 1 by 3, yeah, 1 by 3, and then they will sum up to become 1, no, 2, so 2 by 3, 1 minus 1/3 is 2/3, 2 and 2 cancels out. What am I even doing? Let's write this down properly. So the first term 1 would become y, and y naught plus y naught, it will be 2. So 2y naught, first one is correct. In the second one, there will be a 3 in the denominator, and it will be y naught cubed up above. Since it's an odd function, it will be 2 y naught cubed, so it will be 2 by 3. This is 2 by 3 into y naught. So now if you simplify this, y naught and y naught cancels out, and 2 minus 2/3 is actually 6 minus 2, 4 by 3. And so 2 and 4 would cancel out, give us 2 in the numerator, and this would ultimately be 0.5. So ultimately um is equal to 0.5 meters per second. Okay, the math, is it even properly visible? I'll zoom in a little bit. You can see the math here, right? So we find out after a lot of struggle, and now we will find out what Tm is. So Tm, as we wrote down earlier, it's 1 over into A. We already know and A also we know. So let me reuse this equation here. Add some space in between them. Okay, so we found out to be 0.5, so I'm replacing that with 0.5, and A we found out to be 2 into y naught, so that also I'm replacing it here. We know the functional form of u, which is 0.75 into this thing, so that we will be replacing with this, and ty also has a functional form which was given in the question as 5 plus 95.66 into y by y0 squared. So I'll copy this from it. Y plus y0 squared, and then we also had a minus 47.83 into y by y0 to the power 4. So let's zoom out a little here. So this is how the equation looks like now. Now we have to simplify this big ugly equation, and the way to do that would be take this 0.75 outside, and there is 0.5 into 2 becoming 1, so this will be fraction. Copy this fraction outside. Let's copy the entire thing. Yeah, so the fraction would be 0.75. We can get rid of 0.5 times 2 because it's 1, and the integration would be the same, and let's add a little bit of space here. And there are this is now a product of two terms. Remove this. This is now a product of two expressions which has two terms for the first expression, and there are three terms in the second expression. So this will now boil down to 6 terms if we perform the actual multiplication. So let's write that down. Get rid of both of these. Okay. So first of all, multiplying the entire um, uh, so first of all we are multiplying the entire three of the terms of the second expression with 1, so it will be the same thing. Let's repeat that. So we'll repeat that. Then they will all get multiplied with a minus uh, y0 squared. So first of all, since it's minus, this uh, signs will change, and we are multiplying with y by y0 squared with each term. So the first one will be squared, the second term will become to the power 4, and the third term will become to the power 6. Now let's integrate this entire thing. I'll again copy this equation. Okay. So the first term, we will perform the actual integration. So I'm removing the integration sign now. So the first term, the 5 becomes 5 into y, and y goes from 2 to, okay, and this thing will be multiplied by y naught in the end. So I'm writing that out as well. So we will just deal with the coefficients now. So 5 becomes 5 y naught, and y naught goes from minus y naught to y naught, so that will become 2. So we will have 5 multiplied by 2 in the first term. Then in the second term, this becomes y squared. It's there. So after integrating, we will have y cubed by 3. So there will be a 1 by 3 and a 2 comes in. So this becomes 2 by 3 times 2 by 3. Then comes the second term. This will be y naught to the power 5 by 5. So by 5. Oh, okay, wait. Shouldn't this be 0? No, okay. So we have 2 by 5. Then this term, this is again a cube term, a square term, which becomes cubed. And so this will be a fraction of 2 by 3. Time. So here. This would have been so much more easier if my writing device worked properly. Anyway, then we have this term where it is to the power 4. So this becomes to the power 5 by 5. So this will be 2 by 5. And this is 6, which will become 7. And we will have 2 by 7. So look at this last equation here. So y naught and y naught cancels out. We have 0.75 outside and a bunch of stuff inside. If we perform all the math, then we should get, let me see. So I'll do the math in a calculator somewhere else. If anyone can help me with this, that will be great. So we have 0.75 outside and inside. So first of all, it's 5 into 2, that is 10. Then plus this thing, 95.66 into 2 by 3. Can anyone tell me what the value of that is? 95.66 into 2 by 3. It's something around 63.77, is it? Sixty-three point seven seven. So write down 63.77. Then minus of this thing 47.83 into 2 by 5. What is that? The third term. 47.83 into 2 by 5. 19.13. 19.13. Cool. Then another term is 5 into 2 by 3. That is 10 by 3. Should be around 3.33. Then we have again 95.66 into 2 by 5. What is that? Should be around 20, maybe 30, 40. Yeah, sorry. It's 200 by 5. Yeah, 38.26. Thanks for helping me out. And we have the last one. It's 47.83 into 2 by 7. This should be somewhere around 12 or a little bit more than that. 13.66. Yeah, thanks. And what happens if I take a sum of this thing, this entire thing? $20.03. So after a lot of struggle, here we are. The temperature, this was in degrees Celsius, right? So finally we have this. The Tm is equal to 20 degrees Celsius. It took a lot of time. Thank you guys for your patience. I'm really sorry about today. Yeah, I'll stop sharing and go back to our presentation. This was clear, right? Any questions regarding this one? Okay. Yeah, we are back. So we solved this one. We will move on to the last question of today. That is asking us that consider pressurized liquid water flowing at m dot equal to 0.1 kg per second in a circular tube of diameter so and so, 0.1 meter, and length L equal to 6 meters. If the water enters at 500 Kelvin and the surface temperature of the tube is 510 Kelvin, determine the water outlet temperature. And we have given a expression for turbulent flow through circular pipe as well. The Nusselt number equal to 0.023 into Reynolds number to the power 0.8 and Prandtl number to the power 0.4. Yes, someone has raised a hand. You can unmute and say whatever you want to say. Rishabh Kumar, you have raised your hand. Do you want to say something? You can unmute and speak if you want. please feel free to do so. Oh, okay, no problem. So let's get this last problem done. So here we have flow through a circular duct. The mass flow rate is given, as well as the diameter and length of the tubes are given. And if water is entering at a certain temperature, and it's an isothermal boundary condition, that is, the wall is of the same constant temperature Ts equal to 510 Kelvin, then what would be the outlet temperature TMO? And we have given a certain expression for Nusselt number as well. Okay, so let's start solving this. First of all, we will have to look at the okay, so first of all, this L by D, L is, you can see, 6 meters and D is 0.1. So this L by D would be 60. Right? So that's why we can assume it to be a fully developed flow. So there will be a little bit of a entrance length while the water starts flowing, but it will develop pretty quickly, and most of the pipe is fully developed. So that's why we can assume that the entire thing is fully developed as well. Secondly, we have to check the Reynolds number to see if it's laminar or turbulent. The Reynolds number for you know we can express it in a different way when m dot is given. So how to do that? Let me think about it. So m dot is equal to some u average, u bar, let's say. Okay. So u bar into a into rho. This is m dot, and re is written as u bar into, let's say, d divided by mu. So u bar can be written as m dot divided by rho a, and a itself is pi d square by 4. So we will do all that simplification now. U bar is written as m dot divided by rho a. Rho into a. A is pi d squared. I think 2 is pi d squared by 4. So there is a 4 on the numerator. And this is multiplied by d by nu. And so this nu into rho, I can club them together and write as mu. And one of these d's cancel out with one of the d in the numerator. And finally, Reynolds number can be written as 4 into m dot, 4 into m dot divided by pi mu d. If we simply plug in all the values over here, Reynolds number comes out somewhere around 11,000. Okay, so that's why okay, so here mu is not mentioned, but water is mentioned. For water, this mu is around 10 to the power of the order of 10 to the power minus 6. So that's why this value is pretty high. This is, I won't say equal to, but rather approximately of the order of. You can, crunch the actual numbers and find out as well. So this comes somewhere, pretty high. So that's why uh, the flow conditions will be turbulent, and for turbulent circular pipe this expression is given. We will now use this expression. The nu d is actually h d by k. So h d by k is this Reynolds number, whatever we find out. So this is something around 11,000. I'll take 11,000 itself, and I'll request you to find out the actual one. Okay, sorry, this first thing. So this is to the power point. Oh my god. Let me start again. So this is 0.023 into Reynolds number is 11000 to the power 0.8 into Prandtl number. So for water, Prandtl number is somewhere around 0.7 or 0.8. So you can take 0.8 in this case. 0.8 to the power 0.4. And the value of K for water also you can find out, that is 0.63, I guess. So value of K is 0.63. Oh my god. This is 0.63, and D is already given to be 0.1 in the question. So if you putting all that, the value of H comes out somewhere near 235. This is 2. Okay. H becomes something like this, 230 watt per meter squared Kelvin. Then you have to plug in the expression for the bulk mean temperature in a isothermal pipe. So Tm there is given as T wall minus T wall minus of Tmi, that is the inlet, temperature, into e to the power minus all that we saw. So e to the power minus Px, but since we're interested in the outlet temperature, we will write it as PL divided by m dot Cp. m dot cp into h bar. So this is the exponential part. And if you put in everything, then uh, Tm should come out something like 506 Kelvin. Okay. Any questions? 506.1. Yeah, good. Any questions regarding this one or anything else? Okay, so that's it for today. Thank you a lot. Thank you.
Hello.
I'll have
Hello,
to,
sir.
yeah.
Yeah, uh, actually, I meant to ask this only for the last week, but
Yeah,
I couldn't make it to the class.
yeah.
The solutions of week 2 and 3 are different from the solution that are given in the assignment, sir. Can you please ask someone to change that if possible?
In the
Yeah, in the assignments.
the solution of the assignments. Okay, so for
Ah,
which
yes, sir. Yes.
for which weeks? 2 and 3, is it?
Ah, 2 and 3, sir.
Two
First
and
one is correct only,
hmm.
but 2 and 3 are different from the solutions present in the like assignment and also the solution uploaded that are both are different.
Okay, let me check once. So week
Just,
2, I'm looking at first. So and now let's look at the solution of week 2 as well. Ah, okay, these are different. Okay, I'll let the NPTEL team know. Thanks for pointing it out. Okay.
yeah, thank you, sir.
Yeah. Okay. So thank you everyone for bearing with me today. I was really stuck with a incompatible device today which wasn't working properly. So writing was really difficult. But thank you all for your patience. We will meet again this coming Tuesday and discuss the week six topics and solve some problems together. Okay. So see you on Tuesday. Thank you all. Good night.
Thank you, sir.
Thank you.